Well, now let's look at the operation of multiplication. Well, really, just like addition, you just treat a plus bi and c plus di kind of like polynomials. So basically, when we have a complex number like this, or we have a binomial, when we're multiplying, we're using the distributive property. And you may know this by the anagram FOIL. So we're just going to FOIL this, or multiply it out using the distributive property. And they just remember to convert I squared to -1 and combine like terms. So this is exactly the same process that we use for multiplying just two-digit natural numbers, and it's also the same process we use for multiplying binomials. So this is really nothing new here. So we do first times first, that's a times c, that's the f. The o is the outer product, that's the a times the di, so that's a di. The inner product is next, that's b c I. And then we have the outer product, b times d times I, so it's b di squared. Now remember, so we have the AC and the can be put together here because the I square is -1. So this becomes minus BD. So you get AC minus BD for the real part. And then you can put the I components or I terms together here and factor the I out. So you get AD plus BCI. So ultimately what we define the complex multiplication by being the A plus BI times C plus DI is AC minus BD for the real part, and the imaginary part is AD plus BC, and of course that's times I. Now it turns out that this has a very nice version in polar form. I think before we do that, let's look at an example here. So again, using our example here where we can change A and B and C and D. So we have Z, which is right now -1, -3, and W, which is -2, 1. Let's look at the product, which is ZW, which is this point out here. Well, if we multiply this together, let's check it out. So it's -1 plus -3i times -2 plus 1i. So -1 times -2 is 2. That's the F. The O is -1 times 1i is -1i. The inner product, -3 times -2, that's 6 times I is 6i. And for the outer product, we get -3 times 1 is -3, and then we get an I square. That I square is going to turn that to +3 plus the 2 is 5, and -1i plus 6i is 5i. So we get 5 plus 5i, and you can see that, hopefully, yep, it's graphed in the right place. 5 to the right, 5 up. That's 5 plus 5i. Now, if we take 5 plus 5i, we know that that's 5 times the square root of 2, or square root of 50, which is 5 square root of 2, is the length. Okay? But look what we have here. The original lengths were square root of 10, and the other length was square root of 5. Well, square root of 10 times square root of 5 is square root of 50, and that's the length here. Oh, that's interesting. Now, what about the angle? Well, we rotate around an angle here of about 2.7 radians, and then the blue one is we rotate around about -1.89 radians. If you add those two together, look what you get. You get, well, pi over 4 radians is what you get for this. So it's kind of interesting. So let me hide the. Let me take this down here, actually, and state our conclusion. So our conclusion is that if you, of course, it's just straightforward if you're going to multiply them this way, but there's actually a really nice way of multiplying them if they're in polar form. To get the magnitude of the product, you just multiply what are the coefficients in this form, and the angles, it turns out to be, you're just adding the two angles together, which is kind of why we use this r e to the I theta form, because it works the same as this would be if these were just just regular exponential things. We would multiply the coefficients to to get the new coefficient. And when we multiply these, we keep the same base and add the exponents. And then, so that's the base of E, and this is I theta, and this is I alpha, and this is I beta. That's I alpha. That's I alpha plus I beta, which is I times alpha plus beta. So it works out nicely in this form. And by the way, that E is the special E that we use for our base of exponential functions in the real number system. You know, about 2.7 something. It's the E you have a button for on your calculator. Now let's actually prove that this actually works. So here's our proof. So we're going to let Z be A plus BI. W is C plus DI. So alpha is going to be the modulus of Z, the angle for Z. Beta is the modulus of W, its angle. And theta is going to be the angle for the product. So it's the modulus of Z times W. So let's find the size or absolute value of ZW. It's the distance ZW is from the origin. So that's the size of this product. Well, we know the product from the way we defined it above is this. AC minus BD plus AD plus BCI. So to find its norm or magnitude, we just square each part, the real part and the imaginary part, add them up and square root, Pythagorean theorem. So squaring this out, remember when we square a binomial, we square the first, that's A squared C squared. We square the last, that'll be positive B squared D squared. And to get the middle, we multiply them together and double it. Well, if you look, you've got one each of A, B, C, and D. And one's positive, one's negative, so we get negative 2 A, B, C, D. Should have a D there. Okay. Similarly, when we square AD plus BC, we get square the first, that's A squared D squared, square the last, that's B squared C squared, and we multiply and double it. Again, we've got one each of two of A, B, C, and D, and then we're going to double that, but notice it's positive this time. So now when we drop those parentheses and combine like terms, this ABCD, negative 2ABCD and positive 2ABCD cancel out. And so you get A squared C squared plus B squared D squared plus A squared D squared plus B squared C squared. And it turns out that's exactly what you get when you multiply A squared plus B squared times C squared plus D squared. Let's check it out with FOIL. Let's go from this way back. So A squared times C squared is the first time, that's your F. Your O is A squared times D squared, that's here in this term, the third term. The I is the middle two here, B squared times C squared, that's the last term over here. And the L is B squared times D squared, and that was the second term here. So if you notice, we got exactly what we need. Of course, the square root of a product is the product of the square roots, so that's the square root of A squared plus B squared times the square root of C squared plus D squared. And that is just the absolute value of A plus BI and absolute value of C plus DI, which is the absolute value of Z and the absolute value of W, multiplied together. So the norm of a product is the product of the norms, or the absolute value. The absolute value of a product is the absolute value of the absolute value of the product's absolute value, the product of the absolute values. So in other words, how long is this guy? Well, it's however long this one is times however long this one is, gives you however long that one is. So we're measuring distances from the origin. Kind of nice. So that tells you that if you got r e to the I theta times r e to the I beta, we do in fact multiply the r and s to get the coefficient here, which is just the length, the absolute value or the distance from the origin. Now, to show the angles or adding the angles together, I'm going to find both the sine and cosine here. So I'm going to add the angles alpha and beta together and find their cosine. So we're going to use this identity. Cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Cosine alpha is its x, or its real part over its absolute value. So it's a over norm of z. Similarly, cosine beta is c over norm of w. Sine of alpha is going to be b over the norm of z, and sine of w is going to be d over norm of w. So if we multiply these together, we get AC over norm z norm w, and here we get BD over norm z norm w. So both of them in the bottom have norm z norm w. We can put that together as one fraction since they already have a common denominator, and for the numerator we get AC minus BD. Okay? But norm of z times norm of w, we just proved, is norm of ZW. And so now what do we have? We have AC minus BD over norm of ZW. Well, look at the product here. Where's the product again? Well, here's the product up here. That's the same as the X component, the real part, I should say, over the norm of the whole thing. And so that's going to be the cosine of the angle theta. So we've got the cosine of alpha plus beta is the same as the cosine of theta. Now let's do the same thing for sine. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So we're using those identities we learned earlier. Sine alpha is b over the norm of z. Cosine of beta is c over the norm of w, plus cosine alpha, that's a over norm of z, and sine of beta, that's d over norm of w. So again, you get a norm of z times norm of w for the denominator, and for the numerator we're going to get bc plus ad. I wrote it ad plus bc, same thing. And notice AD plus B, and again, once again, norm of Z times norm of W from our previous step is norm of ZW, and so that, if we look at ZW, again, here's ZW, is this product right here, that's going to be AD plus BC is the imaginary part, and we put that over the size of ZW, that's the sine of the angle. So we've shown that if you take alpha plus beta, you find its cosine, you get the cosine of theta. And if you get sine of alpha plus beta, you get the sine of theta. So that means that theta and alpha plus beta are the same, or at least it's coterminal with that. So theta is alpha plus beta, and so the modulus of ZW is the modulus of Z plus the modulus of W. So pretty cool. So that tells you if they're in component form, it's easy. It's fairly easy to multiply them. You just use FOIL. But maybe it's even easier to multiply them in polar form, because all you have to do is multiply the magnitudes and add up the direction angles. Pretty cool, huh? Looking at our example here, so that shows our example once again, negative 1 minus 3i times negative 2 plus 1i, and we worked out those steps just a minute ago, and that's 5 plus 5i in rectangular form. And because we know these links, their absolute values are square root of 10 and square root of 5. Multiply those to get square root of 50, which is 5 times the square root of 2. And if we add the two angles together, it turns out to be, in this case, we're adding these two angles here. It turns out to be exactly pi over 4, actually. So that's what we get for multiplying these together. So in other words, if we so notice this is a negative angle, so if we rotate from here back around to the axis here, if we rotate in that direction the same amount from where we end up here, guess where we end up? We end up right here along that ray. So that is how you multiply complex numbers.